Welcome to my video on measuring density of copper with an Archimedes balance. What I want to go over first is what is an Archimedes balance and how it works. An Archimedes balance measures density by comparing its weight of an object in air to its apparent weight when submerged in water. So this shows the specimen, the piece of copper we're trying to measure, and then setting on top of a balance scale so we can measure the actual weight. And so when we submerge this copper in water, the object experiences an upward buoyant force. This force equals the weight of water displaced by the object, causing the balance scale to decrease. So actually when I submerge this in water, the scale reading is going to decrease. This all goes back to Archimedes. He was a scientist, mathematician back in ancient Greece, about 250 BCE. And the story goes that the king of the island he lived on basically thought that the crown that he had a jeweler make for him was full of non-gold. Basically, he'd kind of got a low mix of gold, and so he asked Archimedes to figure out if it was real or not. And Archimedes didn't know exactly how to do it, so he used this idea, developed the idea of buoyancy, where he could figure out essentially the density of the object. And he determined the gold crown was not all gold, and then the jeweler paid the price. So Archimedes realized that the volume of an object could be found by the amount of water it displaces, allowing density to be determined without knowing an object's shape. So this is a very powerful technique for measuring density of oddly shaped objects where you can't really measure. It's not like a square or rectangle. Some of the key ideas here is we're dealing with a buoyant force, so that's the weight of the displaced object. In other words, when you push an object down in water, it's got a force pulling it up. The buoyancy force, that's the way ships stay afloat. They displace water. And this force down is the force of the object in the water. And then from that, you determine the volume. So the volume is equal to the mass of the displaced water divided by the density of water. And this is very useful because it's really hard to measure the actual volume of an object. So this allows us essentially to weigh the volume of the object by knowing the density of water. So from that, we can calculate the density of the object, which is just the mass per unit volume. We've kind of done a little trick here. Archimedes developed that the volume can be determined by knowing the weight of the displaced water in this case. So this is the video I want to show you on the actual measurements I did with my little Archimedes scale, and I'll just kind of narrate this as we go along. Okay, so there's my scale. I'm going to zero it. First of all, I'm going to weigh the piece of copper. It turned out to be 28.29 grams. Then I'm going to attach it to the balance scale, put it on there, and weigh it again. And it's 212.21 grams. So that's the dry weight of the scale plus the copper round. So the next step is to submerge it in water. And I had to kind of lift up the scale there to get a good reading. To do this properly. A little cumbersome there, but it does work. Okay, so now I submerge just the copper in the water and let things stabilize. No, you can't see that, but that's what I'm doing. I came up with 209.01 grams. So you can see the actual weight decreased on the scale because of submerging the copper in the water. It produces buoyant force upwards. Now for the results I've got here, the mass of the copper round that was dry, 28.39 grams. And then the balance reading in air with the copper was 212.21, and then the balance reading with the copper submerged in water was 209.01 grams. So the difference due to buoyancy was 3.2 grams. That's the change in the scale reading due to submerging it in water. So the mass displaced was this 221 minus 209, 3.2 grams. We know the density of water is approximately 1 gram per cubic centimeter. So the volume of the copper was 3.2 cubic centimeters. So the density now becomes the mass divided by volume. right here. So that's the mass divided by the volume. 28.39 divided by 3.2 gives us 8.87 grams per cubic centimeter. So that's what we measured. The density of the copper was 8.87 grams per cubic centimeter. The accepted density of copper is 8.96 grams per cubic centimeter. And so very close. So this is a really accurate method of determining density. In this case, it's about 1%. So that's pretty good for a simple experiment. So some of our sources of air, we had air bubbles attached to the copper, which is going to change some of our buoyant properties. Then the scale readings, I had motion, the vibration, scale reading uncertainty. It's not a perfect scale. It's still pretty accurate though. And then the water temperature was slightly different than that would be for the exact measurement of the density of water. But it's very close. So overall, these effects introduce small uncertainties, but do not significantly change the result of measurement of the density. If you do this properly, you get a fairly accurate density measurement. So in conclusion, the Archimedes balance provides a simple and accurate method for measuring density, and you're going to see in future videos I'm going to use it again. Using the buoyancy and basic measurements, the density of copper was determined with an excellent accuracy. So it was a success. I want to thank you for watching.